Rational functions, reducing rational expressions to their lowest terms, and the end behaviors of rational functions. Reducing rational functions to lowest terms is no different than simplifying, except we're simplifying variables such as finding common factors and basically factoring out, no different than what we learned several weeks ago. When I look at this, what we also have to remember is that I cannot have 0 in the denominator. So when I have an expression x over 2 over x plus 1, such as right here, my x can never be negative 1, because negative 1 plus 1 would equal 0. And I can never have a 0 denominator because I can't have 20, 10, 2, a million pieces of nothing. Simplifying, when we look at this to its simplest form, start basic simplification. 6 over 8. That's no different than in the numerator, 2 times 3 is 6, and 2 times 4 is 8. I got a common factor of 2 here. Those cross off. On left is 3/4. Now we got some variables here. 4b to the 6 over 20b cubed. Now I'm going to try to separate this out into similar forms. 4b to the 6 is the same as 4b cubed times b cubed. And then 20b to the cubed is 4 times 5 times b cubed. And what ends up happening here is the 4's cancel out. The b cubes cancel out. I'm left with b cubed over 5. 12x to the 4th over 3x to the 6th. 12 is same as 3 times 4. I got an x to the 4th is left. And then 3x to the 6th is the same as x to the 4th times x squared. And what I have here is I can cancel out the 3's. I can cancel out the x to the 4th. I'm left with 4 over x squared, which is the same as 4 as x to the negative 2. When we reduce, the first thing we want to do is factor the numerators and the denominators separately. Find the common factors and cancels out, since anything over itself is 1. That x squared plus 3x over x squared plus 5x. I could pull out an x out of both of those, leaving x over 3 times x plus 5. Now, I could reduce this x plus 3 over x plus 5, but remember, I cannot have a 0 in the denominator. While x cannot be negative 5, because that would leave negative 5 plus 5 is 0. Now I'm going to make it 0, because in the original form, there's an x squared here. I put a 0 for x squared plus 5x, it's also 0. So even though it's not in the final reduction, we do have to include that in the original form, it could not be 0 either. Let's look at a simple one here. I got 6x plus 20 over 2x plus 10. I could pull out 2 out of both of those, and that leaves me with 3x plus 10 over x plus 5. So basically, to the right here is the graph. But x cannot be negative 5 because that would be a 0. And that's where you have an asymptote right here, a vertical asymptote. X and every 5, it can approach it. It can be negative 4.999 or negative 5.111, but it can never be negative 5 because that would put a 0 in the denominator. Now, this is another interesting one right here. X cubed minus 3x squared over 5x squared minus 5x. I'm going to factor the numerator and denominator. I can pull out x squared in the numerator. And there's my x squared, which reduces it to x minus 3. In the denominator, I can pull out a 5x. That leaves x minus 1. So obviously, x cannot be 1. But that 5x I pulled out here also means it cannot be 0. So I got a vertical asymptote at x equals 1. There's also a point on this curve where x cannot equal 0. It would be right here. It's a tiny little infinitely tiny spot. But x cannot be 0 either because it will not exist in the original form. We're going to talk that's called a hole, and we're going to look at that in a little bit. Now, most importantly, we have to look at the end behaviors of the functions. And what I mean by that is really where does this go from negative infinity to infinity? Where does it end up? I've got an equation here in it's a rational function, 4x to the 5th plus 5x cubed minus 19x all over 2x squared. Well, really, what's most important is my highest functions, my numerator and my denominator. If I put 1 for x to the fifth is 1, x cubed is 1, x is 1. But when I put 2 to the fifth, when I put the x to the fifth, 2 to the fifth is 32. X cubed, that would be 32, not 33. X cubed is 8, and then x would be 2. If I put 3 in for x in the numerator, well, 3 to the fifth is 3 times 3 is 981, is 243. 243, 3 cubed is 27, and then x3 by itself. The point is that that x to the fifth is growing at a much greater rate. 1, 2, 3 ends up being 1, 32, 241. So really, it doesn't matter the growth of these other two. The biggest factor affecting the growth in the numerator is that x to the fifth. I got 2x to the squared in the denominator. That's the biggest one in the denominator. And really what we have here is 4x to the fifth over 2x squared. And that really reduces down to 2x cubed. And that's basically the behavior of this graph right here. We have an asymptote at 0 because x can't be 0. Now here's another interesting one. If I have the same highest exponent in the numerator and the denominator, which I do right here, I got 12x to the fifth over plus 5x cubed plus 19x over 2x to the fifth minus 6x. My highest is 12x to the fifth in the numerator, and the denominator is 2x to the fifth. Well, the x to the fifth or x to the fifth is simply cancels out. I'm left with basically 12 over 2. Cancels it out, which is 6. And what do I have here? I have horizontal asymptote right at that point. Right here. It's a horizontal asymptote, and that is when the highest functioning component of the numerator and the highest functioning denominator are the same. Now, so there's this one here, x over x cubed plus 27. Well, the only x it cannot be in the denominator is negative 3. Because negative 3 times negative 3 is 9, times negative 3 would be equal to negative 27. So that's why it can't be negative 3 because negative 27 plus 27 would be 0 and put 0 in the denominator. And what we have here, we have an asymptote. And I graph this equation at negative 3. And this is what you're going to have when you have a highest degree is smaller in the highest in the numerator than it is in the denominator. Now, more importantly here, when I have a higher degree in the numerator or the denominator, doesn't matter. We want to go at the end being infinity or negative infinity. Let's look at 9x to the fourth minus 5x squared minus x over 3x minus 7. I'm going to cross this off. I'm looking at my highest components. 9x to the fourth over 3x is really 3. 9 over 3 is 3. And then x to the fourth over x is x cubed. So as x approaches infinity, 10, 100, 1000, y gets bigger. As x approaches, that arrow is approaching negative infinity, put in 3x squared, we're still going to get, of course, a negative. Because I have negative 1. Negative 1 cubed is negative 1. That's 3 is negative 3, so negative 10. That'd be negative 1000. So the higher lower my x goes, the higher my x goes, the greater it's going to be as well. Similarly, when I look at negative 2x squared plus 3x minus 7 over negative 6x squared minus 9, cross everything else off except the highest degree in each component of the numerator and the denominator, it's negative 2 over negative 2x squared over negative 6x squared. These cancel out. Negative 2 over negative 6, same as 1 over 3. And guess what? As x approaches infinity, y approaches 1/3. X approaches negative infinity, y still approaches 1/3. It does not matter. I got the same level of exponents here. Now, when I look at this, I got 7x squared minus 2x over x plus 5. I'm going to cross off every other component except the highest ones. 7x squared over 7x, this is 7x. As x approaches infinity, 7x is infinity. 7x approaches negative infinity. It'd be negative 7 times infinity. Now, most interesting is, I'm looking at this one here, where I have negative x to the fourth plus 6x plus 4x in the numerator, and then negative 3x to the fifth plus 4 plus x to the fourth minus 8 in the denominator. Cross off everything else at the highest exponents for the numerator and the denominator. That's negative x to the fourth over negative 3x to the fifth, which is the same as 1 over 3x to the fourth, because those two negatives make a positive here. But 1 over 3x to the fourth, if you look at this as 3x to the fourth, as if x is 1 to the fourth, well, that just equals 1. That just equals 1/3. What if it 1 over 3 times 2 to the fourth? 2 times 2 is 4 times 8 is 16. That equals 1 over 48. So my number is getting smaller. And then, what if I put 1 times 3, 1 over 3 times 3 to the fourth? Well, 3 times 3 is 9, times 3 is 27, times 3 is 81. And then 3 times 1 over 8 times 81 is 1 over 243. So as my x gets bigger, my y gets smaller. It goes from 1/3 to 1/48 to 1 over 243. It approaches 0. It's getting tinier and tinier. Same thing, negative exponent. 1 over x to the fourth, it's still approaching 0, because even my negative exponents become positive because I have an even number here. Now, we were talking about holes before. And when I talk about a hole here, this is basically a point where it cannot exist, even if it's not an asymptote. When I have a function here, negative 2x plus 8 over x squared minus 6x plus 8, I factor this out. I get, in numerator, negative 2x plus 8 is the same as negative 2 times x minus 4. And if I use the PQ method for x squared minus 6x plus 8, that's x minus 4 over x plus 2. Those x minus 4s obviously create something that can be reduced. I have work after the x minus at x equals 2, 2 minus 2 is 0. But where it cancels out, I still have the original component, and I have a hole where x equals 4, as it shows right here. It's not all the way across, it's only at that one point. Here's another hole. X squared minus 9 over x cubed plus 8x squared plus 15x. If I factor this all out, this, as you recognize, the difference of squares, which is x plus 3 over x minus 3. I pulled an x out of all these. Right there, which is x squared plus ax plus 15, which is x plus 3 over x plus 5. Well, these two cancel out. X cannot be negative 5, and x cannot be 0. But even though it's canceled out here, I have a hole where I have an x plus 3 in the numerator, x plus 3 in the denominator. And that's where that hole is, at x equals negative 3. So I have two regular asymptotes, one right here. I got next to the 0, so you can actually see it going up and down. And then right here, negative 5, going up and down. That hole is only at that one point. And either side of it just can't be right there. And that's where we canceled out because it was the same factor in the numerator and the denominator. So the rule of thumb here is we look at rational graphs here. If the x in numerator the exponent in the numerator is less than exponent in the denominator, I'm going to have an asymptote of 0. Because I could have, this would be basically 3 over 4x right here. And that means x can't be 0. It can be anything else but that. If I have equal, I'm going to get a horizontal asymptote. It's 3x plus 1 over 4x plus 1. That's over 3 over 4x. 3x over 4x is just 3 over 4th. Same degree. And basically, I have an asymptote at 3/4. If it's greater, I'm going to have called a slant asymptote right here. Actually, the y equals x squared. Or, y equals x. It's a linear equation. Because 3x squared over 4x is the same as 3/4 x. Or y equals 3/4 x, which is just simply a linear equation. And that's what that slope is, right? The slope is 3/4, as we can see by this right here. And that is what we're going to have called a slant or oblique asymptote. And if it's greater than 1, such as 3x cubed over 4x, right here, that'd be the same as 3x squared over 4, 3x squared over 4, or 3/4 x squared. We're going to have, basically, in this case, a parabola. And there it is. It's with the fraction, it makes it a little lopsided. But it's basically a parabola. So because my highest exponent x cubed is over x, which is the same as x squared. And you really won't have an asymptote. Now my oblique asymptote, basically I've got an equation here. Is that x squared minus 4x plus 4 in the numerator. And then I've got x squared minus 4x plus 4, 2x plus 2 in the denominator. Really all I'm worried about is this x squared in the highest component in the numerator. And then 2x in the denominator. All right, a 2x here. Well, that basically is the same as 1/2. X squared over x is x. So my slope is 1/2. And that's what I have here. For every one here goes 2 across here. So that is not only my asymptote, it's actually the equation of the lines here. Now with a fraction, you get some interesting lengthening. But this is what's going on with this. Use polynomial division to find the asymptote formula. And this is where you divide the denominator into the numerator, which I've done here step by step. X cubed minus 3 divide by goes into x cubed plus 6x squared plus 9x. I'm left with 9x plus 18. So my equation would be, when we reduce down, to be x plus 6. But I have further asymptote also where x cubed minus 3 could never be right here negative times square root of 3.